Well, as mentioned in the previous video, the kinetic energy of an object is the energy it has due to being in motion, and it is defined by this equation. Energy is a scalar quantity, and it is measured in units of joules, abbreviated capital J. The kinetic energy of an object is what we call frame dependent, meaning that it depends on the speed of the object, so observers in different frames of reference will disagree on its value. The kinetic energy of any object will be determined based on how fast you are determining that object to be moving. The terms thermal energy and internal energy are ways to express the aggregate kinetic energy of an object's constituent molecules, and that is not the same as an object's overall kinetic energy. I do recommend that you take the time to look at OpenStack's University Physics example 7.7 and 7.8 that are mentioned on this slide. Those two examples have an excellent explanation of what I mean by exactly this. Let's talk about how the kinetic energy of an object can be changed. If you look at the equation, clearly one would have to change the mass and or speed of the object in order to change its kinetic energy. Let's assume that the mass of an object cannot be changed for now. So one needs to change the speed of an object in order to change the kinetic energy. We know that that means the object has to experience some net force, because a net force must act on an object in order for that object to speed up or slow down. That's how you change an object's kinetic energy. As introduced in the previous video, the way we talk about the energy of an object being changed by a force is that we say the force is working on that object. The working a force does is the topic of OpenStack's University Physics Chapter 7. As it says here, the increment of work, dW, that is done by a force F as it acts on an object through displacement steps dr is equal to the dot product of those two vectors. That means dW equals force dot dr, or force times dr times cosine theta, where theta is the angle between the direction of the force vector and the direction of the displacement vector. The amount of work done over an entire path of motion is the sum of all the infinitesimal dw's along that path. So you would take what we call a path integral. Let's take a closer look at what that path integral from point A to point B looks like. Vectors are used to define work, as it says on this slide, and we see a little dr vector, that's the blue vector. Notice from path A to B, dr, all the infinitesimally small steps you would take to get from A to B along that path, that changes direction as you move from point A to point B along that line. Let's assume that the force vector, the red one, does not change direction as you move along that line. So sometimes theta, the difference between the way that those two vectors are pointing, sometimes theta is going to be really small, sometimes it's going to be bigger. That's what theta is, though, is the difference between the direction of the force vector and the direction of the motion at that moment. If that looks like it could get complicated, well, it could. So let's start with the working done by a constant force, which changes that equation, as you see here, to the force times the displacement times cosine theta, without having to talk about it as an integral. We'll come back and do the integrals, the path integrals, in later examples. So an example without the path integral would be something like this. The work done by a constant force, shown in this image, where the displacement vector is to the right and the force vector is down at an angle. So to calculate the work, you would take the magnitude of that force vector times the magnitude of that displacement vector times cosine theta. Another example would be the person holding a briefcase and not moving. No work is done because the displacement is 0. But what about this person holding a briefcase and walking horizontally? No work is done now because the displacement vector and the force vector are perpendicular to one another. So the cosine of theta is 0. So what I'm saying is, just because a force is applied to an object does not mean that that force is doing work on that object. For another example, let's go back to this block on an incline. How much is the gravitational force between the planet and the block working on the object, working on the block, in this problem as it slides down the ramp? I'll give you that the mass is 1 kilogram, so we can take a actual calculation here. Well, the equation is that the working done by gravity is equal to the force of gravity times the displacement of the block times cosine theta, where theta is the difference between the direction of those two vectors. The force of gravity is, of course, mass times the gravitational field strength, g. So this turns into mg d cosine theta. The force of gravity vector that I'm putting on the screen now points straight down, and the displacement vector points down the ramp. They are not in the same direction, so I do need to know what that angle between them is. I run into a little bit of a problem here because this picture already has a theta equals 37 degrees at the bottom, telling us the angle of incline of the ramp, and that is not the same as the angle between the force of gravity and the displacement vector. So for this particular problem, calling them both theta would be kind of confusing. I'm going to change that theta at the top of the ramp to be a different Greek letter, phi. And so in my equation, I will now say that the working done is equal to the force of gravity times d times cosine phi, where phi is the actual difference between the direction of the force of gravity and the displacement. So now my working done by the force of gravity is m times g times d times cosine of 53 degrees. And since I know the mass is 1 kilogram, g is 9.8 newtons per kilogram, and d is 5 meters down the length of the hypotenuse of this triangle here, I just need to know what cosine 53 degrees is. So I put that in my calculator. It tells me it's 0.6018, meaning that if I multiply all these together, I get that the working done by the force of gravity is 29.5, and of course the units for work are joules. So what about the working done by a variable force? Well, if a force is varying, then that requires you to have some expression for how the force varies. Example 7.4 in OpenStax University Physics shows what that might look like for some arbitrary expression of force as a function of time. But also, I'm hoping you remember this experiment that I did. It showed up when we were talking about force exerted by a spring as it stretches. If a spring exerts a restoring force that increases proportionally to the amount it's been stretched, then the spring obeys Hooke's law, and the graph of force versus displacement looks like this. And the integral of that graph is just a triangle. Algebraically, we might say that the force a spring exerts is easy to write as a function of distance stretched or compressed, so the integral is pretty easy to put together. The work done by the force of a spring, as a spring is stretched or compressed from point A to point B, is equal to this equation here. The working done by the spring is negative because the force exerted by the spring is restoring in nature. Always keep in mind that the force a spring exerts is in the opposite direction of the displacement or distortion that was done to the spring. So if an external force is doing the work, then you would calculate that the external force is doing positive work. But if the spring is the one doing the work, that's going to be negative by the nature of the spring.